This is chapter 4, where we are discussing bending. This is the 29th session overall, and we'll be discussing composite members subjected to bending, including reinforced concrete. This diagram gives us a glimpse of where we are in the overall scheme of things. Here we discuss composite members, where we use the flexure formula to find out stresses in such members. Here we consider a composite beam, which is a beam with a section made up of two or more materials. So in this section, there are two different materials. One has a modulus of elasticity E1 and the other has a modulus of elasticity E2. These two materials can be two different types of steel, or this may be brass and this may be copper, or they may be any two different types. The two or more materials can be arranged in any configuration. Thus, in reinforced concrete, the whole beam is made of concrete with steel bars embedded on the tensile side, perpendicular to the section. We'll analyze composite members in a similar way we have analyzed members of a single material. We'll discuss where the analysis is similar and where the analysis differs. Now consider this as a composite beam subjected to a positive moment. The beam is subjected to pure bending. So the moment in portion A, shown by the dotted lines, and the moment in portion B, again shown by the dotted lines, are the same. We can therefore infer that the radius of curvature of these two portions will be the same. Hence, similar to the beam of a single material, the composite beam bends in the form of an arc of a circle. We also discussed that in beams made of single materials, a transverse plane in the beam after application of the moment remains plane. The same can be argued for a composite beam. So a straight line AB in this diagram will remain straight after application of the moment. We further argued for a single material that the variation of strain is linear with the application of the moment. There's a neutral axis, and for a positive moment, there is compressive strain on the top and tensile strain on the bottom. The same arguments can be given for a composite beam. So also for a composite beam, there be neutral axis with zero strain, and the strain variation will be linear. If there's a positive moment applied, then there will be compressive strain above the neutral axis and tensile strain below the neutral axis. Till now, the analysis of a composite member and a member made up of a single material when subjected to bending has matched. Thus, we have looked at curvature and strain, and in both cases, the analysis is similar. Now, we will look at stress variation and equilibrium equations, and we'll see that here the analysis differs. In the case of a single material, we used Hooke's law to find out the stress variation from the strain variation. Since the modulus of elasticity was the same, the stress variation was similar to the strain variation, though the magnitude of the ordinates were different. Here we have a beam made up of two different materials. So even though the strain variation is similar to that of a single material, the stress variation, which is obtained by multiplying with the modulus of elasticity, will be different as shown here. Here we have taken the modulus of elasticity of material 1 as larger than the modulus of elasticity of material 2. So the stress variation attains the form as shown. After this, for a beam made of a single material, we use the equation summation fx is equal to 0 to find the position of the neutral axis, and the equation summation mz is equal to 0 to obtain the flexure formula. We can use two different procedures, the transformed section method and the formulation procedure, to find the position of the neutral axis and the variation of stress in a composite member. Here we discuss the transformed section method, which is commonly used. The equations summation fx is equal to 0 and summation mz is equal to 0 that were used to find the position of the neutral axis and variation of stress in a member of a single material are equations involving forces. Stresses are not directly involved, but one can say they are indirectly involved. So if we convert the composite member to a member of one single material so that the forces acting on the fibers from the top to bottom remain the same, then we can find the position of the neutral axis and the stress variation. Consider the fiber related to point P, which is in the junction of the two materials. The strain variation is given here. The strain of the two materials is same at the point P. So we can say that epsilon B1 is equal to epsilon B2. Now consider the ratio of E1 divided by E2 as N. Then the stress-strain relation can be written in this form, from which we get sigma B1 divided by sigma B2 is equal to N, or sigma B1 is equal to N times sigma B2. So in this stress diagram, sigma B1 is shown N times sigma B2. Consider the area A1 and let us extend the stress variation corresponding to material 2 as shown here. Then if sigma 1 is the stress in material 1 and sigma 2 the stress in material 2, for this portion sigma 1 is always equal to N sigma 2. Now consider a small element EA. The force acting on this element would be EA into sigma 1. But EA sigma 1 can be written as EA and sigma 2. Hence, if we consider material 2 and multiply the area dA by n, then EAn into sigma 2 will produce the same force. Let us think of the composite member to be made up of fibers infinitesimally thick from top to bottom. Consider the fiber of which dA is a portion. Then the area of that fiber multiplied by sigma 1 give a force F dash as shown here. If in the transformed section we increase the width to NW, then that fiber multiplied by sigma 2 would give the same force F dash. Force is equal to stress into area. Can manipulate the combination of stress and area to keep the force the same. This is what we have done with F dash. So in the portion A1, we can multiply all the fibers by n in the transformed section of a single material so that the forces remain the same in the fibers. So we construct the transformed area from top to bottom so the forces in the fibers remain the same as of a composite member when subjected to a given moment. The width of the portion A1 is multiplied by n, and also the width of the portion A3 is multiplied by n. So instead of these variations, we have used these two variations of equivalent area and stress, which will give the same forces in the fibers from top to bottom. We'll be able to find the position of the neutral axis, and using the flexure formula for one material, this stress variation, we'll then work backwards to find the stress variation of the composite member. Earlier we considered fibers of infinitesimal depth from the top to bottom of the composite member. The equivalent member was made up of one material. The section was given in the equivalent member so that the forces acting on the fibers from the top to bottom was the same as the composite member. Consider now larger areas such as A1, A2, and A3. Let the average stress acting on A1 in the composite member be sigma 1 dash. So the average of these two stresses is sigma 1 dash. Now sigma 1 dash multiplied by the area A1 gives us the force F1. Now consider the transformed section. Let the average stress for this area be sigma 2 dash. Then sigma 2 dash into this area, which is NA1, is equal to F1. So the force in these two cases are the same. It depends upon whether N is grouped with the stress or with the area. As we earlier saw, N sigma 2 dash is equal to sigma 1 dash, and AI1 into sigma 1 dash gives F1 in this case. In this case, we have N grouped with the area. So NA1 into sigma 2 dash gives F1. For the area A3 and NA3 in the transformed section, the forces again are the same. It is given by F4 here. For this portion A2, the stresses and the area in both cases are the same. So F2 and F3 has to be the same. We have divided the composite member into three areas, A1, A2, and A3. In the equivalent transformed section, A2 remains the same as the composite member, but A1 is multiplied by N and A3 is also multiplied by N. We can get the centroidal distance of this transformed section from AA. Let Y1 be the distance of the centroid of this portion from AA, and Y2 and Y3 the distance of the centroid of these two portions from AA. Then YC is given by this formula. Here in the denominator, we have the total area of this transformed section. Once we have the centroidal distance, we can find the moment of inertia of the transformed section. For the three areas, we can find the moment of inertia of the areas about their own axis. Using the parallel axis theorem, we can then add AD square for each of the three areas. The centroidal axis is also the neutral axis of the transformed section and also of the composite member. Knowing the moment acting on the section, we can find the variation of stress of the transformed section. Here, y is the distance from the neutral axis. This is the stress variation of the transformed section. It is not the stress variation of the composite member. Neither this area nor this stress is the same as the composite member. Similarly, neither this area nor this stress is the same as the composite member. In the composite member, we have the stress multiplied by N and the area divided by N. So the stress that we get for the portion AI in the transformed section, we multiply by N to get actual stress in the composite member. And Similarly, with the portion A3. So now we have both the neutral axis and the stress variation in the composite member. The stress variation of the transformed section for the portion A2 is the same as composite member. We earlier discussed that the radius of curvature will not depend upon whether the section is of one material or of two or more materials. So we can find the radius of curvature of the transformed section, and it will give the radius of curvature of the composite member. Earlier, for a single material, this is the equation of radius of curvature we obtained. So here we use the I of the transformed section and the Young's modulus also of the transformed section. Thus, we obtain the radius of curvature and the curvature of the composite member. Till now, we have found the position of the neutral axis and the variation of stress of a composite member using the transformed section method. There is another procedure using formulation to find the position of the neutral axis and the variation of stress in a composite member. We'll discuss this direct procedure of formulation and relate it to the transformed section method. To find the position of the neutral axis for a section of a single material, we use the equation Fx is equal to 0. This equation can be written as sigma x dA integration over the area of the cross section is equal to 0. Consider the composite beam to be made up of two materials. Then it follows that sigma x1 dA integration of the area of material 1 plus sigma x2 dA integration over the area of material 2 is equal to 0. Substituting sigma x is equal to minus y e by rho and considering that the radius of curvature is a constant, we get this expression. We can use this expression to find the neutral axis. We have written this expression in terms of n here. This is the equation of a transformed section. This is the first moment of the portion related to material 1. And this is the first moment of the portion related to material 2 multiplied by n. We earlier used the relation mz is equal to 0 to get the flexure formula for a component of a single material. The relation can be written as minus sigma x y dA integration over the area is equal to m. For a composite member of two materials, the equation retains this form. Substituting sigma x, we get this expression. Here, y square dA integration of the portion of material 1 is the moment of inertia related to material 1, and we can denote it as I1. Similarly, we can denote this portion as I2. Then we get this relation for the radius of curvature. or the curvature. For a transformed section using n, this expression turns into this relation. Here I plus NI2 is the moment of inertia of the transformed section. We have discussed this relation before. We can obtain the stresses by again using this relation. Here we obtain sigma x1 in terms of E1, E2 and I1, I2. Similarly, we obtain sigma x2. In equation 1, dividing by the right hand side by E1, we obtain sigma x1 is equal to minus my divided by the moment of inertia of the transformed section. Also, dividing equation 2 by E1 in the right hand side, we obtain sigma x2 is equal to minus myn divided by the moment of inertia of the transformed section. These equations are the same as the equations we obtained earlier. Here we look at reinforced concrete. This is a reinforced concrete beam subjected to a positive moment. A reinforced concrete beam is mainly composed of concrete with steel bars embedded in the tensile portion. The steel bars are embedded at a small distance from its corresponding edge. Let us take a section of the reinforced concrete beam. So figure 2 gives the cross-sectional view. Consider this axis as the neutral axis. Concrete can withstand compressive stress but is weak under tensile stress. So the compressive stress in the beam will be withstood by this portion of concrete above the neutral axis. Below the neutral axis, the concrete will crack. So it is only the steel rods that will withstand the tensile stress. The ratio of the modulus of elasticity N is given as Young's modulus of steel divided by Young's modulus of concrete. This is the transformed area of this section. The concrete below the neutral axis is not considered since it cannot withstand tensile stress. If the total area of steel is AS, then the transformed area here is NAS. So when a positive moment is applied, this diagram gives the stress distribution. To start with, we do not know the position of the neutral axis, and the central axis is given by this formula. We can find the central axis from a base axis such as AA. However, here we find the central axis from the central axis itself. So YC is 0. If YC is 0, then summation AI yi dash is 0. So here, instead of YC being an unknown, we have turned yc into a known and y dash into an unknown. Y dash is the depth of the central axis from the top layer. So the moment of this portion about the central axis is b y dash into y dash by 2 as given here. This distance is d minus y dash. So the moment is n as into d minus y dash, which is given here. And since yc is 0, the total here is 0. This expression gives a quadratic equation of y dash. Once we know the position of the neutral axis, we can find the moment of inertia of this transformed section. The moment of inertia known, we can use the flexure formula to give the variation of stress in this transformed section. Where the steel bars are located, y is equal to minus bracket v minus y dash. So we can substitute that value to give stress in the transformed section where steel is located. Once we have that stress, we can multiply the stress by n to get the actual stress that acts in steel. We can substitute y as y dash to get the maximum stress in concrete using the flexure formula.